Welcome to Tensor Calculus. I prepared a few slides on why you need to know Tensor Calculus. Tensor Calculus is the subject that you've never heard of before coming here, and if you hadn't met me, you probably never would have heard of the subject, but I keep claiming that it's one of the most important subjects you'll ever get to learn. So I prepared a few slides to try to explain why you, in this case as engineers, need to know Tensor Calculus. It is a little bit of a mysterious subject. Even if you did hear about it and you went to the bookstore and you picked up a book on Tensor Calculus, if you looked through the book, you would probably not be inclined to purchase it perhaps, because it's very different from the things you've come to know before. And maybe it's because it's so different that it is such a useful subject. You might find out that it's the subject that Einstein used to formulate general relativity, and that is its importance. Obviously it is very important in that application, but I think that it's much more important. It has applications in all walks of technical life. And I just want to explain why it's so effective, not so much give examples of its use, but sort of try to explain how it arose and what the main idea behind Tensor Calculus and what makes it so useful. So it all starts with geometry. Geometry goes back to ancient Greece, and it's maybe the beginnings of modern science. Everything starts in ancient Greece with geometry. And geometry was the primary subject that was studied for maybe 2,000 years until the Renaissance and calculus came along. Algebra originated in the Middle East and maybe India. And for a long time there were separate sciences. And here's a quote by Lagrange, who'll figure very prominently in this course. And his statement is, as long as geometry was developing on its own terms and algebra was developing by itself, the progress was slow and the achievements were, let's put it this way, not great. So of course, by not great I mean since ancient Greece. Ancient Greece reached incredible heights, but since then there was little development. And in algebra there were quite important things happening along the lines of solving algebraic equations, second order, third order, even fourth order, right? But beyond that, there wasn't much happening in algebra. And then finally, Descartes came along and he formulated the concept of a coordinate system, which is one of the central ideas in tensor calculus. And what did that enable? That enabled the use of algebraic and analytical methods for solving geometric problems. So that gave a huge boost to geometry, but it also gave a huge boost to algebra and fostered the development of algebra and eventually led to the invention of calculus and all of the wonderful things that have elevated the Western civilization over all other civilizations so far, calculus. So you guys never took much geometry in high school, and I think that's a little bit regrettable. It's a beautiful subject. It develops your brain in a wonderful way. So I will actually devote a few slides to geometric ideas, just to give you an idea of what the world was like before algebra and geometry came together. So what was the world like when there was only geometry? And you will see that that world would be very beautiful and somewhat powerful, but also limited. And then I'll show you what happens when you have too much reliance on algebra and forget about geometry. So maybe you start with geometry, but you formulate your problem in terms of algebra, and then that turns out by itself to not work so well. So we'll need a little bit of a compromise, and that compromise will be tensor calculus. So here's a few problems in geometry. You have to start with Archimedes, who was the greatest geometer of them all. Of course, there was Euclid, and I recommend studying Euclid's elements, and maybe we can even do an independent study on studying Euclid's elements, the fundamental concepts of geometry. But actually, it's a book that's quite easy to study. There's a beautiful framework, very perfectly thought out. But then everything's kind of very simple, and it was really Archimedes who had this tremendous imagination to expand geometry to heights it had not known before, and maybe since. So here's something that's considered one of his greatest achievements. He proved by geometric methods, you can probably barely see it, that if you put a sphere of radius r inside a cylinder so that the radii match and the height of the cylinder is exactly the diameter of the sphere, that the volume of the sphere is 2/3 the volume of the enclosing cylinder. So why is that significant? Here's why that's significant. So of course with calculus, it's a relatively trivial exercise, especially if you pick the right coordinates. If you pick the wrong coordinates, this will be a theme, picking the right coordinate system. And it will become an even bigger theme. Don't pick a coordinate system at all. That's the slogan of tensor calculus. But if you pick the right coordinate system for each object, you can pretty much derive the equations for volumes, find the ratio, and you'll see that it's 2/3, quite easy. So why was such an incredible revelation? Well, here's why. The Greeks were beginning to have the concept of pi, which is obviously the ratio of the circumference to the diameter. And they knew that it was a little bit more than 3. And then it was Archimedes who first got a very accurate estimate for pi. And his accurate estimate was 3.14, maybe 1. Maybe he had 3 digits. And at that time, it was an incredible achievement to construct. He did it by inscribing polygons with a great number of sides, 96. He started with 6 and kept subdividing it by a factor of 2, 4 times until we got to 96. And that's pretty close to the circle. And that gave a very, very close estimate for pi, but not that close, just a couple digits. And that in itself was an incredible calculation. So they know that the area of the circle is pi r squared, and they have an approximation for pi, and then they try to put yourself 2,500 years back, calculate the volume of the sphere. So maybe you put in some polyhedron inside the sphere and you calculate those volumes, and you think that that's the approximate volume of the sphere, and what number would that be? So we know it's 4/3 pi r cubed. So 4/3 pi is a little bit over 4. So you do the circle and you get pi r squared, where pi is a little more than 3. And then you try to estimate the volume of the sphere, and you get something a little bit greater than 4. Right? So the most reasonable thing to believe that the circle has its constant, maybe called it pi, and the sphere has its own constant, right around 4, and maybe called that pi 1. There was no reason to believe that the same fundamental concept appears in both the area of the circle and the volume of the sphere. And of course, this proves that it's the same letter pi, and that number that's approximately 4 is actually 4/3 pi. Right? Because the area of the circle is pi r squared, you multiply it by the height, and then, so from this expression, if the area of the circle is pi r squared, it's easy to deduce that the area of the sphere is 4/3 pi r cubed. And that was maybe, at that point, the greatest unifying observation. So connecting areas of circles to volumes of spheres and realizing that it's the same fundamental constant that appears in both was just an incredible unifying event. But how did he do it? Did he use calculus? No, he didn't have it. Did he use some kind of tricky divine calculation? No. But he was basically able to slice up the sphere and fit it into a cylinder. And his proof was entirely geometric. And this is one of the diagrams that he may have drawn. So I'm not sure where this even comes from, but the Archimedes proof did come down to us. So it survived 2 centuries, which is great. And legend has it that Archimedes thought that this was one of his most important results, and he requested that this diagram, this picture, were put on his tombstone, which I'm sure is a completely invented myth, because nobody knows much about Archimedes or where he was buried or where his tombstone is. But I'm sure that this would sound good on a Ken Burns documentary about Archimedes. So we have that. All right, so the main takeaway from this. So the result is awesome, but his reasoning is pure geometry. Right? There are no coordinates. Forget about coordinate systems. This is 1,800 years before coordinates. Right? Forget about coordinate systems. Forget about methods of algebra. Forget about Arabic numbers. So they use Greek numbers. Roman numerals? Right. So actually Greeks had a more advanced system of numbers that actually took a step back in the Roman times. So it was a little easier than Roman numerals, but they didn't have the full concept of zero and so forth. So it was actually a very difficult calculation, and it didn't rely so much on counting as it did on geometric arguments. So that's one problem. Let me give you another problem. It's called Heron's problem. You guys know this problem? Just first concentrate on the top part of this diagram. So the problem is you have two villages and a straight river flowing by. And where would you want to, and if you need to leave village A, go to the river, get some water, and bring it to village B, and you want your distance traveled to be shortest, which point is it? Where along the line is the point, on the river, is the point to which you would go so that your total path that you will travel is the least? Who knows the solution to this problem? Is this yeah? Who's seeing this for the first time? Oh, okay. Great. So it has a beautiful solution. So you could do this with calculus, right? Call this distance right here x. If the whole horizontal distance between the two villages is L, this is x, this is L minus x. You know this distance, call it little a. Call this distance, call it little b. You can write down the equation, I do it on the next slide. Write down the equation for the total distance, take its derivative, and see where the derivative is 0. That has advantages and disadvantages, so let's talk about both. What's nice about this slide is that there is a beautiful geometric solution. And the geometric solution works like this, and the point of it is to basically appreciate its beauty. So the solution goes like this. Find point C, that's a reflection of the point A, and draw a straight line connecting B and C. And where that line intersects the river, that's the line you want to go to. That's the construction. It's kind of beautiful in its simplicity. And here's proof. The proof is that the segment CP has the same length as the segment AP. So the whole path, BPA, is the same as the length of the straight line, BPC. So if you take any other point, and you look at the length of the path, it will be the same length as going to the point Q and then to the point C, imaginary point C, because the point C is just as away from Q as the village A is. And of course this distance, being two sides of a triangle, is longer than BC. So any other path by the triangle inequality is longer. So that's the point you want to go through by drawing a straight line from B to the reflection of A across the river. So it's a very, I would have never thought of this. You know, Heron probably didn't think of it. I don't know how you come up with a solution like this. It's an extremely beautiful solution, and it's so insightful, and it tells us a lot more. It's actually not so hard to characterize this point. What you see from this drawing is because this angle right here equals this angle, and this angle is the same as this angle, and these two angles are the same. So you look for the point as if it's a point on the mirror. Right? If the river is a mirror, then you go straight towards village A from village B, towards its reflection. So the angle of incidence equals the angle of reflection. That's the point you pick. So among all the points along the river, you pick the one that makes these two angles the same. And that actually makes for shorter distance. So that's geometric solution. Are there any coordinate systems here? No. Are there any numbers, any analysis? No. Pure geometry. So that's the world before Descartes. Now let's look at the calculus solution and admire it for its benefit. So remember the equation for the length? So look at it for one more second and let's go back to the previous slide. So I'm calling this distance x, this distance a. So this is a squared plus x squared. Square root gives you this. This is b. This is L minus x, if the whole distance is L. So this is L minus x squared plus v squared. Square root gives you this. You add them together, that's the full distance. So here it is. What do you do in calculus looking for minima? You take the derivative, and it becomes this expression. I'll give you 5 seconds to take it in. You use the chain rule, followed by the rule for x squared. And then, theoretically, if you didn't have any geometric intuition, and it's important, by the time we wrote this down, we've given up our geometric definition. That, if I'm using the word philosophically speaking, is what's wrong with the analytical approach. Because you write this down, it's not super pretty, right? And its derivative is even less appealing. It has its own power. The power of this is that you don't have to be too intelligent to do this, right? You didn't have to have Heron's geometric brilliance. You know how now in math departments, older faculty are grumpy that, oh, these kids, they only know how to use calculators. They don't understand how to calculate by hand and so forth. I'll bet you in the 19th century and 18th century, there were these older math faculty who were complaining, saying, oh, these young kids, all they do is just use calculus. That makes everything so easy. They don't know how to construct these brilliant, one-of-a-kind geometric constructions, right? All they want to do is write down the function. It's all Descartes' fault. He invented this, coordinate system and combined it with, and then Newton with his calculus, and now look at these kids. All they know is calculus, and they don't know any geometry. It was kind of the same thing. It's that powerful, super powerful. It makes hard problems easy, but it comes at a cost. It comes at a cost of geometric intuition. Is it worth it? The answer is, of course it's worth it, because calculus is calculus. But what tensor calculus will prove to you, that you don't have to give up the geometric intuition. So if we didn't have any geometric intuition, we'd be stuck right here. We would say, all right, now you just have to, for given A, B, and L, solve this. It's not even a quadratic equation. Could I make it quadratic? Yeah, you could make it quadratic. Right, and solve for x. And there you go, you have your solution. So just do this, find your x, and there you go. That's where you would build, that's the path you would take. Is there anything wrong with that? No, but you see, we're sort of lacking that beautiful insight that you have to go to a point where the two angles are the same. That's only here if you know about it. So do you see what I did to this equation? I just put this to the other side, so it became L minus x. And without solving for x, I'm saying that x is such that this needs to be satisfied. And it's only when I flip back to the previous slide that I know that that means that cosine of this angle equals cosine of this angle. So I've recovered the original geometric insight, but I cheated. It's because I knew it was there. If I hadn't known that, maybe I would have noticed it, knowing myself, probably not. So that's the cost of calc. That's the cost of using coordinate systems. That's the cost of using analysis instead of geometry. It's extremely effective. It's extremely powerful. You don't need to be as intelligent, but you're giving up quite a bit. And maybe you don't have to give up all that much. Here's another example, just because we're in this world. Think about this problem. So I actually don't have the formulation of the problem, so let me tell you the problem. There you have a triangle. All angles are less than 120. That's a small detail. So just a normal looking triangle. Don't look at this yet. You have to find a point. It's similar to the previous problem, where the sum of distances to the vertices is the smallest. Find a point where the sum of distances to the vertices, the three distances to the vertices, is the smallest. The answer is the Torricelli point, so I'm calling it the Torricelli problem. And we'll solve it a little bit later today by semi-calculus. We'll use calculus, right? It's problem of maximum and minimum, so you can't resist using calculus. But we'll do it sort of in that in-between world where we do use calculus but don't yet have a coordinate system. But here's a brilliant geometric solution. This maybe I would have found because I already knew solution to Heron's problem. So the idea is, so let's think perhaps it's this point D. So here's what we're going to do here. We're going to take the whole triangle and turn it by exactly 60 degrees. That's what happens. So that's how ABC becomes A prime B prime C. It's this triangle turned by 60 degrees. So the point D becomes the point D prime. So this distance is what it used to be. The distance to the point A is now the distance from D prime to A prime because the whole thing just rotated. And the nice thing is that the distance to the point C, because this angle by which we turned is exactly 60 degrees, so this becomes an equilateral triangle because 60, 60, 60. So this distance from D to D prime is exactly the distance to C because this triangle in here is equilateral. So again, we've achieved the same sort of result here, the same effect, because what used to be 3 different segments going in 3 different directions are now represented by one line with 3 pieces. This is the distance to B, this is the distance to C, and this is the distance to A. So once again, if that original sum was the shortest it can possibly be, this would become a straight line. So the way the actual point is constructed as follows. It's in spirit similar to Heron's problem. You take the triangle, you turn it by 60 degrees. Instead of reflecting the village A, this here you turn it by 60 degrees. You connect the vertex B to the vertex A prime. Okay, so now you have this straight line. So you know that actually, I'm not 100% sure after this how to find this actual point. But this point lies on this line. And if it's over here, let me see.
Well, it's an equilateral triangle, so you just...
No, but how do you get its angle? Oh, you draw a 60-degree angle. There you go. You draw a 60-degree angle, and you keep turning it until these 2 sides become equal. There you go. There you go. And that gives you this point. And if you think about it, in this point, this angle is 60 degrees, and this angle is 120 degrees. So you will find that all of these angles are 120 degrees. So the angle that connects, let me put it this way, the angle at which you see this side is always 120 degrees. So it's that special point inside a triangle so that if you connect it to the vertices, all the angles are 120 degrees. So we'll prove that with calculus a little bit later. But again, the main takeaway here, why I added this slide, number 1, it's cool. But number 2, this is what the world was like before there were coordinate systems and before there was calculus. I'll give you one more. You guys ready for one more? So this one is a real beauty. And it's one of the most fundamental problems, and it's the problem that we will probably solve in the last lecture. Right now I'll show you a couple. Here's what I'm going to show. I'm going to show you a few things. Let me first formulate the problem. Among all shapes of given perimeter in the plane, find the one with the largest surface area, find the one with the largest area. Among all shapes of given perimeter, find the shape that has the largest area. And the answer, of course, is the circle. And it's relatively intuitively clear. If somebody gave you some fencing and had you claim an area as large as possible, but you had only limited amount of fencing, if you only had a mile of fencing, what shape would you give yourself? You obviously wouldn't give yourself a long sliver of a rectangle, right? Because that's not much area. You would push it out as much as you can. So I think circle makes sense. But how do you actually prove that it's the circle? So this is one of the oldest problems. It could be the oldest optimization problem. Its formulation is completely geometric. All right, its solution took a long time. The solution that I'm going to show you, that's pure geometry. It's brilliant. I only learned it on Tuesday. So if we hadn't canceled last week's lecture, you wouldn't have had this. It's so simple. I think it was from 1846 due to Steiner. Someone I've never heard of before, but he liked this problem. Pure geometry. So number one, it's beautiful. Number two, this is a very important problem, so that's why we're going to look at it. And number three, just keep thinking, well, I never would have come up with a solution, ever. But just thinking how A, beautiful, but B, tough the world was before you could use analytical methods to solve problems. So here is a solution, abbreviated. A few things you need to know about circles as shapes. So circles have the following property. If you pick 2 points, can you see it's a little pale, but you can probably see. If you pick 2 points on the circle, on the circle, then whatever other point you choose above it, let's say, and you look at this angle has a name. But it will be the same for all points over here. It will be the same angle. So you see these two angles are the same, but even if you pick the point over here, you can kind of imagine that angle and it'll be the same angle. Right? It's kind of an amazing fact. So the set of all points from which a given segment is seen at a certain angle is a circle. It's kind of a very nice fact. It's actually really easy to prove why that is so. Because this angle is always half the central angle. That's not hard to show, I'm just sort of giving you a glimpse. So if you go to the center of the circle and draw the same angle, connect the same points, this angle will always be twice this angle. And because the central angle is common for all of these, you can show it for any one of these angles. It shows that any angle is the same. And if you look at the right angles, then that segment is the diameter, right? Because this is 180, the central angle is 180. I forget what this angle is called, it has a name.
Subtended.
Subtended angle. So the subtended angle is half the central angle, and because the central angle is 180, the subtended angle is 90 degrees. So when you talk about 90 degrees, that means you're looking at the diameter, not just some segment, but the diameter. So that's all you basically need to know. And here comes the proof, really in just a couple of steps. First thing you need to realize, I actually don't know, everybody, whenever you read about this proof, it's always mentioned as step 1. I'm not seeing 100% how this applies, but the argument is that it needs to be convex shape. So let me just, on the side here, show you why it needs to be a convex shape. Because if it happened to be a shape like this, like not convex, what you would do is draw this line, keep this in. And I'll start again. Should I pause for editing? I'll draw the line first. There you go. So if it was a shape like this, you would just reflect this portion of it. It would make the area larger while keeping the perimeter. So of course, think back to you staking your plot. It would be silly to make it concave, because by making it the same shape but convex, you could use the same amount of fencing. You would just make the area larger. So that's the thing number 1 to realize. So it has to be convex, kind of like this. Thing number 2 to realize, that if you pick 2 points, A and B, so you let this be our suspected shape, pick the points A and B, so that this is half the perimeter, and this is the other half the perimeter. So here's the statement, if it's half the perimeter, then if you connect them by a straight line, it will also cut the area in half. If we're looking at the optimal shape, if you have a line that cuts the perimeter in half, it will also cut the area in half. Why? Because suppose it doesn't cut the area in half, suppose the bottom area is larger, then again by flipping it, now you have a new shape whose perimeter is the same, right? Because this was half the perimeter and that was half the perimeter. So the perimeter is the same, but the area is larger. If this was the larger half area-wise, then by flipping it and now calling this the 2 halves, the heart, you now have another shape of the same area. Excuse me, of the same perimeter but larger area. So that's why the statement is true, that if a straight line cuts the perimeter in half, it cuts the area in half. So that what's nice about this is that it reduces it to half the problem. We can now only have to look at shapes with 2 points on a straight line, right? And now the problem has become find the shape of given perimeter of just this part of the arc with points on the straight line that has the largest area. And here's the final circle. So let's prove that that's half a circle, a half circle. So what we will prove is that if you pick any point, so suppose that's that arc. The statement goes that if you pick any point on that arc and draw the angle connecting it to the endpoint, it will have to be 90 degrees. So that's what I'm about to show. That if this shape is indeed optimal, which of course this one cannot be, but we're making a different point here, then whatever point you pick, this base will be seen at the 90-degree angle. And that of course proves that it's a, excuse me, went the wrong way, that it's a semicircle, because the semicircle has that property, that the base is seen at the 90-degree angle. And here's how the proof goes. So suppose it's not 90, in this case it's greater than 90. Just focus on this triangle. So keep these parts, call them ears. Keep them rigid. Now just focus on this triangle. I can make the triangle larger by keeping the lengths of the sides constant, but making the angle closer to 90 degrees, right? If you look at triangles with the lengths of sides fixed, right? Do you see this triangle? For what angle does it have the largest area? So here the area is 0. Here the area is 0. Now remember, area is the product of the sides times the sine of the angle between them, times 1/2. So the triangle is largest when it's 90 degrees. So that's what's using here, what we're using here. So if it's greater than 90 degrees, just close the sides in a little bit. It'll lift it up. You have to keep these points on a straight line, right? It'll lift it up, but it'll make the area larger. It'll make the combined area larger. The perimeter is the same, right? Because the perimeter came rigidly with you. The perimeter is just the sum of these 2 arcs. So the perimeter, when we did this slight closing of the triangle, was unchanged, but the area got larger. So that's what happened if the base was seen at any angle other than 90 degrees. So for every point on the optimal shape, the diameter is seen at the 90-degree angle, which means that the problem we're talking about here is the problem of minimum surface area. So the experiment that you see in the picture is 2 metal rings dipped in a soapy solution, held together and then pulled apart. And the soap film will assume the shape of least area. This is modeling of soap film according to Laplace. And the question is, what is this shape? Euler wasn't thinking about soap films, perhaps, but he just asked it in abstraction. What's the area of revolution? What's the surface of revolution that has the smallest area? So his approach did combine calculus with geometry, but he was thinking very geometrically. And he was only looking at the profile of the shape and thinking what profile would give me the smallest surface area if I were to consider shape of revolution. So he only considered r of x. So imagine an x-axis here, and the distance to the surface is r. So the only function that he was considering is r of x. So in a sense, he introduced cylindrical coordinates. And in the cylindrical coordinate system, the whole shape was given by just one equation, r of x. And by developing the calculus of moving surfaces, which for the purposes of this discussion are slightly beyond the scope, we'll do calculus of moving surfaces. Excuse me. We'll do calculus of variations a little bit towards the end of the course. But here's the equation he came up with, an ordinary differential equation, deeply nonlinear, which is always the sort of thing you get when you're dealing with minimal surfaces. And he actually solved it. So hyperbolic cosine was a solution to this problem. And it's beautiful. But it's also a little bit limited, because it would not have worked even if the rings were in slightly different planes, if they weren't parallel, right? Or if they were, well, actually, if they were shifted, there's still a solution that maybe he would have found. I'm not sure if the rings were shifted, but if the rings were any shape other than the circle, his method would not have worked. It really relied on geometric insight and the symmetry and the ability to reduce the problem to just a one-dimensional profile. But this is really a genius attempt at combining geometry with calculus. That's for this shape. Now what happens for more general shapes? So Lagrange took a stab at it. So Lagrange did something extremely powerful. He really, true to his statement about the marriage of algebra and geometry, he just asked a much more algebraic question. So it's inspired by geometry, but he approached it really from the analytical point of view, and his method was more analytical than Euler's method. It didn't rely on the symmetry or geometry, but again, it had some tremendous benefits and some drawbacks that we should acknowledge. So he said, I'm going to consider functions that are graphs of x and y. So what did he do? I'm almost tempted to say, what did he do wrong? It's blasphemy to ask what Euler or Lagrange did wrong. They didn't do anything wrong. They made remarkable breakthroughs. But can we analyze the advantages and the disadvantages of a particular approach? And the answer is yes. So the advantages, of course, at that point far outweighed any disadvantage. The potential disadvantage being possible lack of geometric intuition. Given the breakthrough that this was, that's not what they were thinking about. So if this is the really equation of the surface, then I don't know if you remember from multivariable calculus. I hope you don't. Trying to memorize these formulas is a thankless task that destroys your confidence. I could never remember them. Tensor calculus will tell you how to write these things out reliably without having to remember them. That's one of the least important, but very nice side benefits of tensor calculus. But this is what it's given. This is the equation by which area is given. And then what Lagrange figured out how to do is how to work with analytical expressions like this, and how to go from an equation that gives area to an equation that minimizes area or maximizes area, or does something, characterizes what shape has a certain value of area and so forth. Right? And he derived this equation, which of course is very difficult to solve. It's a partial differential equation. It's deeply nonlinear. It has squares. It has triple products. We don't know what it means geometrically. Going back to Euler, we don't know what this equation means geometrically. We know where it came from. But remember, think back to Heron's problem. What was nice there is that we figured out the solution, even when we did the analytical approach with equations. But then we could go back to geometry and say, well, actually what this is saying is that the solution is such that the two angles are equal, right? That was very nice geometric insight. So suppose you solve this equation, and you find that the solution is the hyperbolic cosine. What does it tell you about the shape? It gives you the shape. But do you have any extra insight? Do you know if it's a maximum or a minimum? That's the question that always comes up. Is it a maximum or a minimum? So you solve this, you get the hyperbolic cosine. Is it a maximum or a minimum? For it to be observed in nature, it has to be a minimum. So what's the criterion in geometry? It's very difficult. I don't even know if it's possible with pure geometry methods. So going back to the previous slide, when I showed you the property of a circle being the largest area, what if you wanted to take that to 3 dimensions. I'm actually now arguing the counterpoint just because I forgot to mention. What's the shape of largest volume given the total surface area? It's the sphere. But is there a geometric proof of it? No. So it really invites calculus and analytical methods. And now we're using calculus and we're seeing something slightly dissatisfactory. We're much further along than we were without calculus, but there's just, how do we know if it's the solution to this is a maximum or a minimum? Without analytical methods, we don't know, I don't think. What about more complicated shapes? So, if we take Lagrange's approach to the 3-dimensional problem I just mentioned, we kind of know in that case the answer is the sphere, but how would you prove it? So for that you would have to go to spherical coordinates, so the next slide is a mess. But that's kind of my point, that the slide is a mess. You go to polar coordinates, where the radius is a function of theta and phi. And I'm considering this tremendous simplification that it doesn't even depend on phi. It would not have fit on the slide if I also allowed it to be a function of phi. So I'm only considering axially symmetric shapes. So once again, shapes of revolution. But now it's not the minimal surface area, it's the largest area. It's the largest volume given the surface area. And the surface area is given by this integral, which I didn't remember and figured it out in 1 second as I was preparing the slide. And what's the volume? I think it's this form. And then you derive the differential equation by Lagrange's method. So this method of working with equations without thinking about where the equations came from is Lagrange's achievement. And you get this equation, which makes me nervous just looking at it, right? Because if you actually want to see the actual equation in terms of all partial derivatives, you would have to open these parentheses, get rid of these parentheses, which use the product rule 4 times. So there would be 4 terms. You'll have a power to the 3/2. And then you can actually see right here that f of theta equals constant. In other words, sphere. Constant radius. In other words, sphere actually satisfies this equation. But But what we notice, and Lagrange probably noticed, and was probably deeply disappointed in seeing this, that that's just how nature works, is that the equations are so cumbersome to actually solve them, which is a tremendous effort. So here we can guess that it's a sphere, and kind of check, knowing that f of theta equals constant satisfies. But if you didn't know that, or if the problem was slightly different, just slightly different, add gravity on a substrate, something like that, it would become a problem that's impossible to solve. Going back to Lagrange's equations, I think the first solution, the first non-trivial solution to this problem came in 1840. And it's not a knock against these equations. These equations are what they are. You know, these equations, Lagrange discovered them, but God gave them to us. You can't blame him for the complexity of these equations. It's just a hard problem. But forget about solving this equation. What does this equation mean geometrically? What does it say about the surface? Is it a minimum or a maximum? Can we extract any sort of qualitative characteristics? It's really the qualitative characteristics that move the world forward. You know, I have an audience of engineers and a few math majors, right? So engineers don't care so much about maybe. I'm going to insult the whole world of engineers. But for engineers, I think it's more important to be able to solve a given problem. Hopefully it already fits in the existing framework, and you just have to actually find a solution. That would be one application of these equations. But conceptually, you want to understand it and maybe move it forward and apply it to other problems. For that, you need more insight. For that, you need more geometric insight and physical insight. And all insight here is lost. And there was actually a young Frenchman, his name was, forget his first name, Meusnier. Meussnier, French guy. He was actually a general in Napoleon's army, and he died in battle. He did all of his work when in his 20s. And he said that what this is really saying, and what Euler's equation is really saying, and I never read his work, but I read somebody who read his work. He was, the way apparently he wrote his works was, of course, Euler did everything. And Euler must have known about this, but he never wrote it down, so I'm writing it down for Euler. So what this equation is saying, and what Lagrange's equation was saying, geometrically speaking, it's saying that the surface's mean curvature equals to 0. Mean curvature. So it's this concept, I think it was introduced by Euler. It will be central to this course. It's my favorite object. I know you can see it, but there is, on the slides you can see, there is a B alpha alpha embedded into these slides as a watermark. That's the tensor calculus notation for mean curvature. If I were into tattoos, that's what I would tattoo on my arm. B alpha alpha. It's the absolutely most central object. It arises in the problem of minimizing surfaces, which has everything to do with fluid films. It's the gradient of area, in a way. It's one of the most fundamental objects. So what Masnier figured out is that what these equations are saying is that mean curvature equals 0. Such a simple statement. Right? We'll define mean curvature. Right now you don't know exactly what it is, but it's a measure of how much the surface is curved. So mean curvature equals 0. So it's kind of strange. I'm going to use another phrase that sounds like blasphemy, that Euler and Lagrange missed it. But that's what it kind of appears, that this beautiful geometric insight that, was missed by such greats. Why? Why? Here's the most important thing. Why? Let's analyze why. So the conclusion that we'll come to in the course of our exploration of tensor calculus is they picked a coordinate system too soon. Right? It's not fair to pick a cylindrical coordinate system. It was for that particular problem. For the problem of this shape, it's called the catenoid. For the catenoid shape, it was the right coordinate system, but then it could only answer the question of the catenoid, of surfaces of revolution. This is not the right coordinate system. Why should it be Cartesian coordinate system? And why should we limit ourselves to surfaces that can be represented as graphs of x and y? Most surfaces are not like that. If a surface goes like this, it can no longer be represented as a function of x and y. These are wrong coordinates. If we want to answer this question generally, forget about geometrically, with geometric meaningfulness, just generally, this is the wrong coordinate system. And this is the right coordinate system if we want the answer to be the sphere, but in general, it's the wrong coordinate system. And it's not so much that they picked the wrong coordinate system, it's the fact that the discussion started with the choice of the coordinate system. When you start your discussion by choosing your coordinates, you're doomed, because you end up with expressions that have as much to do with the coordinate system as they have to do with the problem you're solving. And by analyzing the equations, you're not able to tell, am I looking at a feature that's a property of the coordinate system, or am I looking at a feature that's a property of the problem? So our future takeaway will be, don't pick a coordinate system. That's the brilliance of tensor calculus. You obviously want to use coordinates, just because it's the sort of power you cannot ignore. The power of calculus you cannot ignore. So a lot of people have said it's a direction in science that's really at odds with my aesthetic. I cannot criticize it on its merits, but I can say that I disagree with its aesthetic. To completely not introduce coordinate systems ever. There's a school of thought that introducing a coordinate system is distasteful, and that things need to be purely geometric. You can still use calculus in the sense that I'll show you. But no, don't introduce a coordinate system, because why? So I don't find that that's enough of a compromise. It leads to a lot of ugliness. You're about to see on the 2 slides down. The grand compromise is, let us use a coordinate system. That's, as you're learning tensor calculus, that's the framework to keep in mind. Our discussion will start by saying we have a coordinate system, but we will never, ever, ever say which coordinate system we're working in. We'll be working with all of the coordinate systems at once, and we'll save ourselves from dealing with artifacts of special coordinate systems. So I'll just show you in terms of algebraic complexity what can happen. So mean curvature equals 0 is the characteristic of a minimal surface. What another fundamental operator is the Laplacian. You worked with the spatial Laplacian in your homework, but there's a surface Laplacian. We'll learn about that. What happens when you apply the surface Laplacian to mean curvature? Something you do quite often in your analysis. If we go back to Lagrange's coordinates, so Cartesian coordinates, z equals f of xy. I believe it's the next slide. You can't see it, which is fine. So it's however many lines you're seeing, that's how cumbersome and impenetrable the expression becomes. So we'll denote this and be able to do a whole lot with it by just writing the Laplacian of mean curvature. Here's how we'll write it, a very compact expression. And you will actually learn that those are not just symbols. That's an algorithm for computing it in any coordinate system. But you're able to do a whole lot, probably just about everything you want to do with that object, without introducing a special coordinate system, by just working with that symbol. That's tensor calculus. So what you're seeing here, so we started with the world of geometry, beautiful but limited. The world of analytical methods, super powerful, but at a cost of losing geometric insight and intuition, and leads to completely impenetrable expressions whose meaning, you'll give up work. If you had to work with this expression, you'd give up, right? That's actually what happens in most challenging problems. You would think that people are smarter than that and they would just find methods that are pretty, but in actuality what happens, you pick a coordinate system, you do the first variation analysis, you get something maybe a little big, but I can work with it. You go to next order, you get something like this. And you give up on the problem. Right? If you have mastered tensor calculus, you never encounter expressions like this. You encounter expressions like this. And they have all the meaning and power of expressions like this, organized in such a way that expressions never get big, because they're organized by geometric insight. You keep the pause for editing. Was that the phone number? So what tensor calculus allows you to do is carry out all of your analysis, right, but maintain geometric insight. Each expression will have geometric insight. Why? I'll sort of explain it later. So what you're seeing here is the other extreme. Right? A lot of calculus, no geometric insight. So we need a balance. And that balance will be tensor calculus. And you will find, looking back, that until you really knew tensor calculus, you didn't really know multivariable calculus. You were working with multivariable calculus, but you never saw the geometric concepts behind it. You never knew how to interpret your expressions. It's when you combine it with tensor calculus, it's really the true marriage, what Lagrange was talking about, of geometry and algebra. And it happens at a very specific compromise in terms of dealing with coordinate systems. It acknowledges the need for coordinate systems, but really allows you to work to use all of the benefits of the coordinate system without running into the unwelcome artifacts of the coordinate system. So it's really maybe the perfect medium of algebra and geometry. So I think I have one more slide just to, I was just talking about these benefits. Let me see if I've covered them all. First one I covered, enables the use of coordinate system. I mentioned that. Look at that. Provides this, all right. So this you will see a little bit further. So we'll actually come up with expressions. So you computed your Laplacian as your homework. In Cartesian coordinates, it was one expression. In spherical coordinates, it was a different expression. In tensor calculus, what we'll do is be able to develop expressions that actually look the same and work the same and lead to the same algorithm for calculation in all coordinate systems at once. And that's the algorithmic nature of tensor calculus. These expressions, like the one you see over here, are not funny symbols. You'll know exactly what to do with them. They're all actionable. With all of these symbols, you will be able to do calculus with them. It will sort of take you back to your calculus days, where you start with the left-hand side, you write derivative of, and you proceed and you use the rules, right? And there are very, very few rules. Really, addition, multiplication, and then one additional rule called contraction. That's what this says, based on just a couple of operations and one derivative operator, one differential operator. You can see that it's concise. You saw what Laplacian of curvature looked like in a particular coordinate system. That's what it looks like generally, so it's very concise and extremely powerful and keeps the geometric insight. And I don't know if you've ever taken vector calculus. I hope not, because vector calculus is a subject that should be extremely beautiful, and it is in many ways, unless it's abused. So there's, I guess this is the gradient of a dot product. That's what this is. And I know what this means only because I know tensor calculus. But I can easily think back to the days when I didn't know tensor calculus, and I remember looking at these expressions and having my heart filled with despair. What, I have to gradient, what? Like, that was my thinking. What is this? Do any of you know what this means? Gradient sub u of... How's this better? I don't even understand, right? That's how you should be thinking about this. And then this is curl of a cross product equals, all right, so this is divergence. Well, what the hell is this? What's the transpose of a vector? And what's one vector written next to a different vector? What is this object? I don't know. There have been efforts, successful efforts, to endow these expressions with meaning. Maybe it's called the modern language of geometry. I'm mocking it a little bit. For my purposes, for the range of problems that I deal with in my research, it's not necessary to go to that level of formalism. So even if we just look at this, right, we can count how many different operators there are. Gradient, dot product, another gradient that we don't know what it means, curl, cross product, divergence, transpose of a vector, we don't know what it means, but it should count as another operation. Then writing two vectors next to each other in an apparent product, right? I can't visualize that project, but that's another operation. And so all of this, just to hang on to the idea of let's not introduce a coordinate system. What you don't have here is coordinate system. This is calculus combined with geometry without the use of coordinate systems. Talking about vectors and not their components with respect to a basis. So you run into this problem of needing to have too many operators. Actually, these are operators which you don't know what to do with them. You don't know how to calculate in a particular coordinate system, which is what you would need to do if you're thinking about computer implementation. There are rules for a couple different coordinate systems, but not for a general one. Did you enjoy your homework of translating the Laplacian from Cartesian coordinates to spherical? That's what you would have to do in every single instance. If you're working with a coordinate system that's natural to your problem and you have to interpret this product, you would have to go from Cartesian coordinates to whatever coordinate system you're dealing with for everything. Right? The whole point of your homework was that it's not a pretty thing and not something you want to do. In tensor calculus, there is none of that. In tensor calculus, you just get expressions like this. So you may or may not like it. There was a prominent geometer by the name of Cartan who really didn't like this. He said too many indices. He called it orgies of indices. And I can kind of, in this expression, I find it personally appealing, because I think these indices are dancing, and there's a lot of movement in these, and they're pretty. So I really enjoy them. This is proof that the determinant of the product of two matrices equals the product of determinants. It fits in one line. That's a side benefit. The greater benefit from the algorithmic point of view is that there's nothing but products and summation. Nothing but product, just one operation. It adds, tensor calculus adds one more, a derivative, right? You need to take derivatives. So where is the balance? Like, what do you prefer? So for me, I prefer this by a long shot. This makes me shiver. And it will also makes you feel like your professor is smarter than you, right? Because if you see this in class, your professor understands it, and you don't, and you feel like you never will. And the truth is that your professor doesn't, right? Because I don't understand how anybody can understand it. So that's what Hermann Weyl, great German geometer and analyst, was saying in this quote. So I'll just let you read it, I won't read it, but that's exactly what he was talking about. So maybe I'll read parts of it. Endless profusion of names and symbols, that's what I was just saying. That you need a lot of operators. You have to give them different names. Curl, divergence, Laplacian. Was there one more that I'm missing? Gradient. Right, in tensor calculus, we won't have any one of those terms. I'll use them just to relate back to these terms, but you don't really need them. You know, and it's all in the name of avoiding coordinate systems. And he thinks that we should do something else, and that something else is tensor calculus. This is a quote from his book called Space, Time, Matter, where he introduces tensor calculus and Einstein's general relativity. So that's the book that I recommend very highly. Okay, that concludes the presentation on why you need to know tensor calculus. Thank you for your attention. You want to stop?